Welcome to the Thinking Cats. Due to lack of funds, we no longer have tables or desks.
Please stay tuned for the entire show. We need the funds.
And today's topic is light and optics.
So much fun.
If you're still watching, here's Michaela.
Today's first topic will be about the wave. Okay, so this part of the wave is called the amplitude. And that can be either how far up or below it is from the equilibrium position. Now, another part of the wave is the trough, which is the bottom part. And the top part of the amplitude is called the crest. And a whole wavelength consists of this point at the beginning, right here, starting all the way from down there, all the way to right here. And that is what makes up a wavelength, which can be represented by this symbol.
Okay, so we're going to be doing a ray diagram of a convex. Wait, is this a convex lens? Okay, yeah. So we'll be doing a ray diagram of a convex lens. So first, you're going to draw a line from the top of the image straight out into the center of the convex lens. And then you're going to take that line and take it straight through the outer focal point and all the way down. Then your second line, you're going to take from the top of the image and just go straight through the middle of the lens and all the way down until it intersects with the first line. And for the third line, you will go from the top of the image to the focal length and then to the bottom of the lens, and then from there you'll go straight out until it intersects with the first two. And then your new image will be inverted, larger, and real, and on the opposite side of the lens facing down. Then if you're going to do the same thing for a concave lens, you have to do it a little differently. So your first line you will take to the center of the lens, and then from the center of the lens, instead of going through the focal point, you will reverse it so that you create a line from this focal point to this intersection all the way up. So that line will go here along this path. Next, you take from the top of the image into the center of the lens, and then from the center of the lens, instead of continuing down, you do a straight line all the way across right there. And that is your second line. And then for the third line, you're gonna go like you would go through the middle of a lens, just like you did in the first lens, and this one will just be the exact same thing. And so where all three of those intersect is where your new image will be. And this image is going to be smaller, upright, and virtual because it is on the same side as the original image.
Get off here. So today we're going to be talking about focal length, magnification, Snell's law, and wavelength. First is the focal length equation, which is 1 over distance to the object plus 1 over distance to the image equals 1 over the focal length. Now distance to the object is the distance to an object, the vertex to the object, and distance to the image is basically distance toward whatever is on the other side, what's shining through the lens, either concave or convex. Next is the magnification equation, which is hi-ho, easy way to remember it, but that stands for height of the image over the height of the object. This is also equal to negative distance to the image over distance to the object. Okay, so Snell's law. This is used to describe a relationship between the angles of incidence and refraction. Basically, if you have light going through an object like glass or diamond or whatever you want. Light refracts, and here you can use this formula: n1 sine theta 1 equals n2 sine theta 2 to find either n or the what's it called, your theta. Next we have wavelength. Here on this side we have one end open, where so if you have something like this, it's 1/4 of a full wavelength. A full wavelength is like this. So as you can see, this here is just 1/4 of that. So to find the length, you would do the wavelength divided by 4. Here we have 3/4 of a wavelength. It'd be that section. And so here you just do 3 wavelength divided by 4 is equal to the length. Now here we have both ends open, which is different from one end open. And to calculate the length, you have to do for half a wavelength, pi over 2 equals length. And here we have a full wavelength, and that is just the same as the wavelength, sorry. And yeah.
So the first part of the problem is asking us to draw a ray diagram. To begin, we know that the object is represented by this arrow, and the second focal point is right here. The first focal point is right here. Now to draw the first ray, we go parallel to the x-axis all the way up to this lens. And then we go past the first focal point and down. That represents the first ray. For the second ray, we will go past this second focal point all the way down to this mirror and then straight out parallel. And then finally, for the third focal point, we are just going to go through the center. See this green colored pencil all the way up to there. And our image is now formed by the intersection of these 3 rays right here. We know that the image is inverted and it is smaller than the original. And to calculate the position of the image formed by the lens, we will use the mirror lens equation, which is 1 over the distance of the object plus 1 over the distance of the image, which is equal to 1 over the focal length. And the distance of the object is given right here, and we know that it is 45 centimeters. So we do 1 over 45 plus the distance of the image, which is what we are trying to find, and the focal length, which is given to you right here, which is 15 centimeters. And you will need to do 1 over 15 minus 1 over 45 to calculate the distance to the image, which is 22.5 centimeters. Now, to solve the next part of problem B, you need to use the magnification equation, which is height of the image over height of the object is equivalent to negative distance to the image over distance to the object. Now, we are trying to find the height of the image. We know the height of the object because it's given right here, which is 8 centimeters, and it's equal to the distance of the image, but it's negative, which we found in the previous problem, 22.5 over 45, which is given to you right here. We know that as the distance of the object. And to find that, we will do height of the image times 45 equals negative 22.5 times 8. You multiply these two, divide it by 45, and the height of the image is negative 4 centimeters. Now, it asks us to describe what would happen to the image if the lens, if the top half of the lens were blocked so that no light could pass through. Now, we know that all of the rays will cross at the same point. And part of the rays that go through the top half will be reflected back, since now the top half of the lens is blocked. So there will be less light that is bent, but the same image will still be formed and it will be less bright. So that is how you solve the free response for this unit.
Da-da-da-da! I am superposition! Okay, so let's start with finding out the principle of superposition, shall we? Now, on the left here, we have this good constructive interference. So when you have the principle of superposition, you take your waves, wave 1 and wave 2, and you add them to make a bigger wave. Ta-da! But when you have constructive interference, you take one wave and one wave. But when the destructive interference strikes, you have the first wave and the second wave, and they cancel out, and there's nothing. Dun dun dun. On the left, we have an oil slick, and on the right, we have those beautiful bubbles we all enjoy so much. So, let's see. Let's start with the bubble. Goodbye, oil slick. So, you have a beautiful bubble right over here. But if you look closer, and I mean really close, you'll see that these bubbles have different angles of refraction. And so we all know air has 1, and then you go through this tiny little film, and it has 1.5 approximately. And then we have your air again. So what happens to light rays when they pass through bubbles is that some of them get reflected off, some of them go in, and since this is a higher index of refraction, they bend a little bit, and some of them bounce back off. But they have to be in phase. So, my children, in phase means they're constructively interfering, and out of phase means they are destructively interfering. And then they go back, and some of them go back into air, and some of them reflect back. So there's your soap bubble. So, for the soap bubble, we have our lovely equations for constructive interference and destructive interference. And with soap bubbles, you can only have m's of positive values and nothing below 0.
Go.
And on the other hand, we have a lovely oil slick over here. Ta-da! And if we look closer at that, we'll see that they have double layers. So the first layer is air, which has an index of refraction of 1, as we all know. And the second is an oil slick, a little bit of oil on top, the film, which has an index of refraction a little higher. So some light bends and some reflects. And so with the oil slick, again, it has another higher index of refraction. So the waves have to bend a little bit more and then go back out. And with oil slicks, for constructive interference, this is our equation. And for destructive interference, it's a half. This is our equation. And so you'll notice between the two equations right here, they're switched around. So for bubbles, to have constructive interference, they have to be half a wavelength apart, and for oil slicks to have constructive interference, they have to be a whole wavelength apart. And that is because of their differences in their index of refraction. And now, last but not least, we have interference and diffraction patterns. So first we're going to start with Young's two-split experiment, And for all interference and diffraction patterns, the light source has to be monochromatic and coherent. That means they all have to be one color only, and they all have to be within the same phase length. And what we need to realize is, in these experiments, each light acts as a point source, a whole new wavelength. So each of them will go, and depending if they're half a wavelength or a wavelength apart, they will produce a series of bright and dark fringes. And if you look on a graph, they'll have bright and dark fringes, all equal, a little bit more towards the middle, but so we have that. And the equations for bright and dark fringes are, ta-da, constructive. It has to be x max equals d sine theta equals m lambda. And for these, m can be 0, plus or minus 1, plus or minus 2, any whole integer. And for destructive, you'll realize they are half a wavelength apart to do destructive interference. As we know from the principle of superposition, if you add things half a wavelength apart, they will cancel out and become 0. And we have our one slit interference, and that's a little bit more difficult because they have tiny minimums and maximums here, but they all get dwarfed because most of the light is going here. So you also have a series of bright and dark fringes, but it'll be a maximum in the middle. And you will find for these that is the pattern for constructive interference. D sine theta equals m plus half times lambda. And to find the max, it is m plus half lambda length over d. And for destructive interference, d sine theta equals ml, x minimum equals m over lambda l, m times lambda over d. And you will also find that in in one slit experiments, it's very important that the m can never be 0. And the reason the m can never be 0 is because you'll see in 0, a lot of the light goes towards here, so the tiny minimums and maximums here are actually dwarfed by the giant amount of light going there. And there's your interference and diffraction. Go. And last but not least, we have interference and diffraction patterns. And we have Young's one-slit experiment and two-slit experiment. So for the one-slit experiment, for all these actually, the light has to be monochromatic and coherent. That means it can only be one color, and all the wavelengths have to not be affected by time, the phase change. So for the first one point source, the light in the middle has like the greatest, because all of the other like little what do you call it? Cut.
That's okay.